Good morning, everyone. Good afternoon, everyone, or good evening. So my name is Budiman Minasni. I'm from the University of Sydney. So I'm a member of the 4 per 1,000 scientific and technical member. So it's a pleasure to welcome you to our webinar series. This is the third scientific series webinar of the 4 per mil. So what is 4 per mil or 4 per 1,000? So 4 per mil or 4 per 1,000 is an international initiative, or what we call a source for food security and climate. It was launched by the then Ministry of Agriculture of France on the 1st of December 2015 at COP21 to demonstrate that agriculture, in particular agricultural soils, can play a crucial role where food security and climate change are concerned. With the support of solid scientific basis, the 4 per 1,000 initiative invites all partners to state or implement some of the practical actions on soil carbon storage. So the ambition of the 4 per mil initiative is to encourage stakeholders to transition towards a productive, highly resilient agriculture based on the best management on lands and soils, creating jobs on incomes, ensuring sustainable development. The 4 per 1,000 has a vision that we will have a worldwide healthy and carbon-rich soils to combat climate change and hunger. So we are going to have a webinar this afternoon on the measurement, reporting, and verification of soil carbon. So it's a very timely subject because end of this week, there will be a COP28 in Dubai, and of course, soil carbon will be part of the conversation. So to begin with, I'll introduce the first speaker. First speaker is Professor Pete Smith. Pete is a professor of soils and global change at the University of Aberdeen, and he's the science director of Scotland's Climate Exchange and the director of food systems for the Scottish Food Security Alliance. Pete's research is on global change climate impacts on soils, ecosystem, agricultures, and land-based options to mitigate climate change effect. So over to you, Pete.
Thanks very much, Buddy. I'll just share my screen. So I'm just going to talk a little bit about MRV, monitoring, reporting, and verification of soil carbon change. So the one way to measure carbon, of course, the best way is through direct measurement of soil carbon. You can do that with field sampling and lab analysis. So this is the gold standards for accuracy, and you can use things like combustion analyzers to get a direct measurement of the carbon content. But it does require destructive field sampling, extensive sample preparation, laboratory analysis, and it can be slow, costly, and labor intensive. So there are some alternatives to this, new methods that are in development and being used. But Alex will talk about these novel alternatives in the next talk. So I'm not going to focus on this. I'm going to focus on the other aspects and what else we can do to use models, remote sensing, and other data sources that can contribute towards a framework for monitoring, reporting, and verification. A couple of years ago, we published a paper which was looking at MRV for soil carbon change, and we tried to pull together all the different components that could form a framework for modelling. So the first one is using long-term experiments, which I'll go into. I'm going to go through each of these in a bit more detail over the next 15 minutes. So the first thing you can do is take long-term experiments. The second thing you can do is have shorter-term experiments, for example, that are measuring fluxes and occur only over days, weeks, just a few years. And you can use these to develop and calibrate your models. So you see over in the bottom left-hand corner, soil organic carbon or greenhouse gas models, which can be used then to upscale your estimates of change to the landscape scale, using spatial data and activity data. And you can also use remote sensing as an input to this. So I'm going to go through each one of these in turn, but all of these components exist to some extent around the world. with different intensities of measurement and data in different regions. But all of these can contribute, can supplement our direct measurements to form an MRV platform that can be used to determine soil carbon change. So that was the graph that we came up with in that paper, and at the same time, Keith Poustian was writing a paper which came up with a much nicer figure, but exactly the same sort of. This was in convergent evolution, if you like. So this was Keith Poustian's group, which was looking at the quantification of soil carbon, and again they got the long-term experiments, the models, the spatial data, remote sensing, activity data, and going forward to making projections and simulations of soil carbon for monitoring, reporting, and verification. So we both came up with these independently, but it was great to see this paper after we'd published the other one, and Keith saw ours after he'd published his, and we saw that we'd come up with largely the same format for a framework. So let's have a look at each one of these in a little more detail. So the first component is long-term experiments at benchmark sites. So these are on different land uses. They have different treatments within the same land use. For example, there could be agricultural long-term experiments which have different fertilization treatments, or different other practices, different organic amendments. And you have long-term soil organic carbon measurements, which take place over decades. So maybe tens of years, decades. Some at Rothamsted, and in other areas over 150 years old. But you can also have chronosequences where you don't have direct measurement. So you can put together, you can reconstruct a time series where you've got space for time substitution. When we look at where these long-term experiments are, this was a paper that we published back in 2012, looking at the distribution of land use change experiments. Each one of these little dots on the figure is an experiment. So panel A shows the long-term experiments with land use change, evaluating the change in soil carbon. In panel B, these are the distribution of tillage experiments, evaluating the impact of tillage on soil carbon stocks. And at the bottom is the distribution of experiments evaluating different agronomic practices on soil carbon stocks. What you can see is that there are a lot of experiments all around the world, but what you can also pick out on all of these figures, I think, is the concentration of experiments in North America, South America, Europe, and to some extent Australasia and China. So this is going back to 2012. This could be updated, but we haven't updated this figure. But what you can see is there are very few experiments in the tropics and subtropics. This is an area where we lack data. But it shows that there are some experiments around which we can use to improve our models and to make to check that we understand the dynamics of soil carbon. The second component that we can look at are the shorter term experiments. And these may be nested within the long-term experiments, but these are measuring shorter term fluxes. So these are really useful for investigating processes, developing new tools, and for calibrating models. So these sorts of experiments are things like FluxNet. So these are sites where you have eddy covariance equipment in place that's measuring the CO2 and other greenhouse gas fluxes in and out of the system. And as of 2012, this was the FluxNet site network, and you can see that we have flux towers all over the world. Again, not so many in the tropics, but tropics and subtropics. But this is a bit better for FluxNet sites than it is for long-term experiments, the distribution in the tropics. And flux sites have grown significantly in the last 10 years or so. So if we updated this figure, it would now look even more densely populated. But we can use these short-term and long-term experiments to calibrate and develop our soil organic carbon models. So we can either use the models to develop tier 2 emission factors, so emission factors that just slot into the IPCC tier 1 methodology. to determine soil carbon change, or we can use them directly and apply them spatially using a tier 3 methodology. If we have other data, if we have spatial data to run the models, we can run them over the landscape, anything from field level to 1 kilometer resolution all over the world. So this gives us a very powerful tool for assessing what's happening with greenhouse gas emissions and soil carbon change. So there are a bunch of models that we could use. We can use simple models, such as statistical regression models, at the simplest. Then we have the models that are just concerned with the soil. So these are models like Rothsea and ECOS. And then we have ecosystem models such as Century, DNDC, and many other models. So this is just the example showing Century. But these models then can be tested against soil respiration data, isotope natural abundance data, flux data, isotope pulse labeling data. These are all examples of short-term experiments. And then this long-term experiment network, these are the long-term experiments that were available from SOMNet back at the turn of the century, back in about 2000. And we can use all of these to test our models. So we can perform model evaluation, and we could get an estimate of uncertainty and the performance of the different models for measuring these fluxes. And these are just a couple of graphs from model evaluation papers showing the difference between the models in their simulation of soil organic carbon. And what this evaluation does is it allows us to improve the process description using short-term data, and we can then go back to the process and retest the models with new independent data to check that they're working well and to validate them for use in upscaling. This is just an example. This is the ECOS model, which is similar to the Rothsea model. I don't want to go into the details here, but it shows that the carbon is conceptualized as being in different pools, and you can simulate all the fluxes under aerobic or anaerobic conditions, and you can model the carbon dioxide flux, methane flux, and the turnover of soil carbon. It's got a coupled nitrogen cycle, which is shown over here on the right of the figure. So we've got all the nitrogen processes, so we can also look at nitrous oxide emissions. This is just one model. Another model is DayCent, the Century model, which many of you will know. So this conceptualizes also soil organic carbon as passive, slow, and active pools, and has a complete carbon cycle, including the plants. And this is the DNDC model, which is just a different conceptualization, but again simulating the soil organic carbon turnover. So we can use these models if we have adequate spatial data to drive the models. We need climate data, we need soils data, we need land cover data, for example. And when we look back in 2012, and we've done an update since then, these are some of the land cover data and the organic carbon density. We now have excellent databases available all around the world, some down to 1 kilometer resolution or even 300 meter resolution. And we can use these to run our models to initialize the models and to then run them forward. But we also need the activity data. What we're trying to do is simulate soil carbon change after a management change or an intervention. So we need data on what management changes have been made. So we can use this activity data is best collected at the field level. So if we can use the activity data that's collected at the national level from statistical agencies, they collect farmer returns where farmers have to record many of these management activities in order to get subsidies under things like the single farm payment in the European Union or the Conservation Reserve Programme. They have to document it to get their subsidies. So we can use that data and couple it with the models, and use that to drive the models, to tell the models what what management change has been implemented on the farm, and then we can simulate changes in soil organic carbon. We can use number 6 is remote sensing, and we can use remote sensing to verify the activity data, because you can see from satellite whether a field has been ploughed or not. so we can verify tillage data. We can get extra input about inputs, for example, from estimating NPP, and we can get activity data, remote sensing data on the soils directly for some of the components. But for soil carbon, we can't yet do that from satellite with any degree of accuracy very deep in the profile. But this is some of the data that we can use. We can get tillage and crop residue coverage. We can get crop type and crop cover presence, rather, and we can record flooding using these remote sensing data. Or we can get estimates of LAI, canopy N, or gross photosynthesis. And we can use these to run models using data assimilation. We can use these to update our projections and predictions from the model, and then we can run those forwards and run it using real data to calibrate the model as it's running. And lastly, we've got these spatial resampling surveys, which can be used to ground truth and to verify the changes that we're modelling. So these are the sorts of things that we have in various places in the world where we have repeat surveys. This is an example from England and Wales with Pat Bellamy's paper that was published in Nature back in 2005, showing some resampling that was done in 1978, going back to the same sites in 2003, and documenting the soil carbon change. So this is great additional data for model verification to check that your models are working over these longer timescales. So altogether, we can put these together into a verification, monitoring, verification, and reporting program to supplement the direct measurements of soil organic carbon, so that we can upscale our estimates to give it estimates at larger spatial scales, such as for example, at the whole farm level, or landscape level, or even up to national. This is an example of the REC-Soil program, which is a program that's been put together by FAO of global soils. And this is an example where all countries can submit their estimates. This is using a version of ROTC, the Rothamsted carbon model, to estimate changes, what's possible for changes in soil carbon. So do go and check out the REC-Soil webpage. It's the first attempt to put together a framework, a global framework that can be used for monitoring, reporting, and verification. So I'll just finish by saying that I think MRV is one of the biggest challenges to implementing soil organic carbon change as under the 4 per mil initiative. And it's one of the biggest challenges that prevent farmers from doing this and from gaining the credit that they deserve. All components of this MRV framework exist to some extent, but it's uneven globally and they're not integrated. So all of these have to be brought together into an integrated framework to allow us to monitor, report, and verify soil carbon change. And FAO's REC-Soil program is an opportunity to bring many of these things together, especially in developing countries. I think there are great opportunities for robotics, AI, machine learning, data assimilation, and advanced modeling. So for somebody who works in modeling like myself, there are great opportunities here, interesting and exciting opportunities to apply some of these newer techniques to help us move forward with an MRV framework. But the question, measurement or modeling, I don't think we can say we need measurement or we need modeling more than one or more than the other. We certainly need measurement because the modeling is nothing without it. We need both and lots of other things. But I would say as a modeler, don't rely only on models. Please, please, please make sure that you ground truth your estimates with direct measurements wherever possible. I'll leave it there and I'll hand over to Alex, who'll talk a bit more about the measurement of soil carbon.
Thanks, Pete. And we'll hand over to Alex. Before that, I'd like to introduce our next speaker, Professor Alex McBratney. Alex is the Professor of Digital Agriculture and Soil Science at the University of Sydney. In fact, Alex graduated from the University of Aberdeen. So his research is on transforming the knowledge of soil composition and function providing farmers, natural resource managers, and policy makers with new tools to map soil properties from individual farmers' fields up to the global scale. So Alex is a member of the Australia's Emissions Reduction Assurance Committee, which is responsible for soil carbon accounting in Australia. Alex holds a patent for measuring soil carbon on a portion of a landscape. And his current research is on developing a framework for soil security assessment to sustain soil functions and services to preserve planetary systems and human well-being. Over to you, Alex.
Thank you, Budi. I'm just going to share my screen. Just like to thank Pete for what he said. I guess what I'm going to say is 100% complimentary, with an E in the middle, to what Pete said, and complimentary as well. Just a little bit of background. I haven't given a talk about soil carbon internationally since COP15 in Copenhagen, so that was an interesting time, but I'm glad to see things have moved on considerably. So we've been working on trying to figure out how to do soil carbon measurement since around 2008-9, and before that I was very much interested in participating in the whole idea of digital soil mapping and global digital soil mapping, which we started around 2006. So all of that plays its part, and I think really feeds into some of the things that Pete was saying. So in Australia, we have a formal crediting system for all kinds of carbon, and part of that is soil carbon, and we have formal procedures for that. So part of what I say today comes from that. So any money that comes from the government for soil carbon is through a measurement and modelling process. There are no subsidies for agriculture in Australia. So practice-based methods alone don't generate any kind of payments. So that's part of the philosophy behind the Australian approach. So let me, okay, I'm going to give you a fairly simple, almost too simple run through, but I do this on purpose, I think. So we all know about soil carbon sequestration. How can we put more carbon into soil and keep it there? Or how can we demonstrate? That's the first problem. And the second problem is how can we demonstrate that we've done that? And that's really what the measurement, reporting, verification is about. And in this talk, I'm going to concentrate on the second part, but I will come back for 5 seconds to the first part at the end. So a few more points about soil carbon. The reason why we're doing it is it's beneficial to the ecosystem and to agricultural productivity. I think it's important for everybody to realize that in the field, out there in the real world, soil carbon is really quite variable across the landscape. So it's not something that's very smoothly varying, but it does have a discernible pattern. And I guess part of the problem we've had is that some people think it's too variable and therefore too difficult to measure and get a reasonable uncertainty or a reasonable precision. I think it's also important to understand that the pattern itself, understanding the pattern, spatial pattern, temporal pattern, helps with deciding management options, helps with deciding how much sequestration, and it also helps with designing measurement techniques. And I think an important area or an important recognition is the bigger the area, the larger the variation. So you got a small area, you got a small amount of total variation. got a larger area, much more variation, and the more observations that are required. So these are quite simple concepts, but I think they're worth knowing. Here's a map of soil carbon that we generated recently. It's a map of, I think it's a map of 1990, but we generated it recently. So it's not a prediction, it's a post-diction. But we do this kind of global space-time soil carbon assessment, and there's a reference to a paper there. And of course, going back to what Pete said, we do use a bit of mechanism here, a bit of mechanistic modeling and a bit of machine learning, and we stick the two together to give us these kind of predictions. So this is roughly at 250 meters for the whole world, and we're doing it on an annual basis. If we look on this map of Australia, you'll see a little red asterisk. So I'm going to that place there, which is in New South Wales in Eastern Australia. And this is a map of carbon stock to 30 centimeters for an area of probably 200 kilometers by 200 kilometers. And you can see the variation there. We go from 20 tons per hectare in some places to 125 tons per hectare, down to 30 centimeters. You got all kinds of sandier and heavy clay soils in this area. And then we're going to the little place called Nowley, which is one of our farms that belongs to the University of Sydney. It's not a research farm per se, it's a commercial farm. And the important thing here to realise is that the coefficient of variation, standard deviation divided by the mean of the carbon, in this case concentration, varies with the area. On the log scale, it's roughly linear, or if you look at it if we look at the area on a linear scale, you get that kind of curved distribution. So the CV increases with area, and that's something that will affect her measurement accuracy and so on, depending on the size of area, how many samples you have to take. But the fact that it's non-linear means that as you get bigger and bigger areas, you don't need to take linearly more and more samples. It's non-linear in that way. So there is an increasing return when you get to bigger areas. And this is some data from that farm where we measure bulk density. This is just for the not 7.5 centimeters. We look at the standard deviation and the mean and this coefficient of variation of the bulk density. We'll notice that it's only around, the CV is only around 20%, whereas the total carbon is around 73%, and the stock is around 50%. And this is, so one of the things that it's important to realize in it, and I've looked at lots of other places, particularly in North America, that the bulk density varies much less than the carbon concentration. And when we come to estimate the stock varies a bit less than the carbon concentration. So that's useful in the end when we try to estimate stock in efficient ways. But something to bear in mind for this farm of 2,000 hectares. The coefficient of variation for bulk density is about 1% per square kilometre and about 3% per square kilometre for the stock. So about 3 times. So to audit soil carbon change is fairly simple. You just measure the total amount of soil carbon at time T1 and its uncertainty. Now, how you do that, we'll come to in a second. All kinds of ways. And then we can measure the total amount of carbon at time T2 and its uncertainty. And the normal difference between T2 and T1 is around 5 years, because most of us soil scientists realize that it's very difficult to detect change with this uncertain background in less than about 5 years. So that's a kind of practical thing. And the carbon stock change is simply CT1, CT2 minus CT1, and in this case it'll be the carbon stock. And the uncertainty is, particularly if you don't measure it at exactly the same places, it's the sum of the uncertainties at the two times. And that's a simple way of calculating the uncertainty. But you need to estimate the uncertainty. And what I'm suggesting is formal probabilistic sampling designs, such as stratified random sampling, are best for obtaining the uncertainty. They're not the only ways, but they are. They give you good estimates of uncertainty, and they can also be optimized to do that with economic efficiency. And in this case on Nowley, here's a stratified random design that for the farm. And in this case, we've done the stratification. People say, well, what do you use to stratify? Well, my suggestion to everybody is to use the best estimate of the soil carbon stock. The best prior that you've got, use that to stratify, because this idea that using the best guess of what you've got to stratify, I think, actually works in practice, and we've done lots of work to show that. And I think that gives us four main measurement methods, if you like, and this complements to a large degree what Pete said. I'm really talking here about tier 3 methods for creating carbon credits, but other applications apply. But the four main methods would be some kind of stratified random sampling. There are various approaches to that, and lab measurement. So that's create a stratification, go ahead and create a sampling design within the strata, which is random in this probably, and then go and take the observations and take the samples back to the lab and make measurements. The second one is virtually the same, except that we've got stratified random sampling, but now we're not going to take anything back to the lab, or very few. We're going to do field measurement. How are we going to measure this carbon stock in the field? And then we're going to take some small amount of observations, which are independent of the stratified random sampling, for calibration and lab measurement, so that we've got a calibration for the field measurement. I'll come back to that. And then the indirect methods, and it's pretty much what Pete said. We're going to do remote sensing via empirical models. And there, once again, you're going to need to take a little bit of sampling for calibration, and take some of it back to the lab for creating that calibration. So you've got a calibration sample and measurements of those calibrated observations. And finally, the process modeling, which requires the same thing. You're going to need some calibration sampling and some measurement of those observations. And of course, you could hybridize 3 and 4 between remote sensing and process modeling, between empirical modeling, mechanistic modeling, and sort of neural network modeling. Now, the measurement itself is of soil carbon stock, and that's generally the mass of carbon by the volume of soil. So it probably requires a measurement of the soil carbon concentration and the soil dry bulk density. As I said earlier, the soil carbon concentration tends to vary a lot more than the bulk density. Now, if we look at various methods for doing that, in the lab, we can have things like the LICO method, bulk density by old-fashioned taking bulk density course, or taking cores in the field and doing gravimetric measurements. All of that's quite cumbersome and quite expensive, but it is accurate or precise. In the field, we can use things like spectroscopy. And what tends to be used is something in the range of the UV visible near infrared. But there are other techniques such as inelastic neutron scattering, which is a radioactive or radiation kind of method. And we could get estimates of bulk density in the field using gamma densitometry. Some people are not keen on using active radiation in the field, so some of these methods are less preferred. Remote sensing is largely about reflectance from the soil surface. There's a little bit of penetration, and that's one of the issues about remote sensing, that you're really modeling, you're really doing the modeling based on changes in the soil surface or the vegetation above the soil surface. Bulk density itself is from a prior, is probably from digital soil mapping. The process modeling is usually some sort of kinetic pools, or it might be less mechanistic than that. And bulk density probably from pedotransfer functions. But I notice that these days people in their modeling model a stock as the pool rather than the carbon concentration. I think the important thing to realize with all these methods is that they have different uncertainties and they have different relative costs. And these are some numbers that I've come up with myself, and they're not set in concrete by any means, but roughly speaking, I think the uncertainty around the lab measurements are the least. But even then, the uncertainty is still not tiny, probably around 5%. Bulk density is actually difficult to measure, even though it's less variable. And the relative cost, if we make the relative cost of the lab measurement 1 unit, the field sort of measurements that we talk about using spectroscopy are probably 3 times more uncertain. And the relative cost here I'll put down as 1/3, but I've got evidence that it's probably 1/10. Remote sensing. Now, this is where we get into more difficulty. I suggest that the remote sensing is around 50% uncertain, like the process modeling. They're kind of similar in a way, and the relative cost I'll put down at 3%, but it may be much less than that. And I think that's why I put question marks beside them. I think the other issue that we need to consider about remote sensing and process modeling, to what degree do we have bias? And that's why so it's not just about the precision, but it's also about the bias, so the overall accuracy. But I think they all have their part to play. So I think there is a bit of an unknown here, a bit of work needs doing on the cost per unit area versus the uncertainty, because that in the end decides which methods we should be using at which scale. And of course, there is a scale effect, as I showed earlier. Some methods may be better at the farm scale and some at the national scale. So this is farm Nowley again, and these are the estimate. These are the priors for the carbon stock and the uncertainty. And in the methodology that we use the stock and the uncertainty together to give us our stratification, and we ended up with a strata, and we end up with observations. So that allows us to estimate the total carbon stock for that farm at one time and its uncertainty. It's the confidence limits on that, and I think that's the important thing. Now, when it comes to how to measure carbon in the field, what looks most promising at the moment are the visible or UV visible NIR spectrometers. And this is one that we've been using, a spectropenetrometer that we've been using and developing. And there's a paper there where we've used it, and you can see, I guess the advantage of this kind of method is that you get lots and lots of observations to which you can fit a depth function. So you can get good estimates all the way down the profile, and then get an estimate of the overall stock. We can calibrate, we're trying to calibrate both for carbon concentration and do some physical measurement for bulk density, but it's also possible that we can calibrate directly for stock. So that's the UV visible spectropenetrometer. I've also been doing some work with an American company and the US Soil Health Institute, funded by the US Department of Energy, to develop this hand drill penetrometer. So basically, you can see at one end there's a hand drill, in the middle there's a spectrometer, and then there's a drill bit, and at the end of the drill bit you see an auger, and there's a window there that picks up the spectra, and using that you can quickly estimate soil carbon down to 35 or 40 centimeters. So it works very well in the beautiful Luesial soils of the Midwest of the US. When we don't know whether it'll work in Australia, where our soils are a lot drier and harder, but it's a good technique, a good technology. I think sampling. So here we're looking at the sample density for the same cost, and you can see that we can get a much higher sample density for the same cost using the NIR or field method against the lab method. Now, the trade-off here is the NIR method is less precise, the lab method's more precise, but for economically, you might be able to take more samples using the NIR method, and because there's real natural variation out there, less precise methods can actually be more cost effective. So there is actually an advantage in having spatial variation in this case, particularly, and that's something that I think needs to be understood. And just a few comments about how to use the uncertainty. And this is particularly applies to how we might use it in Australian conditions, but it would be the same across the world. Anybody creating credits or for soil carbon, the cost per hectare alone is an incoherent concept without considering the uncertainty. So we hear people saying, "Oh, we can do the measurement for 50 cents a hectare or $3 a hectare." That doesn't mean anything unless you know for that particular method what is the uncertainty associated with that. And the way we would like to use the uncertainty is to discount the amount of carbon sequestered, or to discount the recognized amount of carbon sequestered, which is a better way of saying it, and the associated payment. So credit, and one way to do it is to credit the lower Z percentile of the stock difference. So we could say Z equals 90. So credit the lower 90 percentile of the stock difference. And you get that from the variance or the uncertainty at the two time periods. So just a simple example, if we're auditing soil carbon change and we had an actual stock difference of say 1,000 tons, let's just simple units, 1,000 tons in this case. Method A, the uncertainty is 5%. So the uncertainty in the stock difference is 50. So the lower 90%, and the lower 90% is minus 82. So the carbon stock difference credited is 918 tons. Whereas if we had another method where the uncertainty is 30%, then the Z, the lower 90% means we lose minus 400, we lose 494 tonnes. So the stock difference credit is 506 tonnes. So we're building in here the uncertainty of the method to give different amounts of crediting. The other way that this works, of course, is in some situations, people don't apply this kind of quantitative approach. They simply pay less for the credits. They credit the same amount, but the value of a credit in method B, using method B, might be 10% of that in method A. So there's a couple of different ways of doing it, but the way I would prefer is to discount the amount credited via the uncertainty. That gives us an impetus for measuring the uncertainty. In terms of methodologies, going back to what Pete said, there is a methodology, I think, which is stratified random sampling, remote sensing, and process modeling. And I think you can probably use the calibration sampling observations for the first part, stratified random sampling, to actually calibrate the remote sensing and the process modeling. And we're currently working on 5. I think 5 is the way forward, to put all of these together. We get very good observations, very good estimates and from the stratified random sampling. But the remote sensing and the process modeling can fill in some of the spatial gaps and can decrease the uncertainty to some degree. And it's just a question of what the economics and practicality of all that looks like. But I think the future looks very much like 5. Anyway, in terms of the methodologies, each of the 5 methods that I've talked about should have a formalized methodology. And any acceptable methodology, to my mind, requires a formalized, measurable uncertainty. And perhaps some of this idea comes from the fact that I sit on a committee for the government that approves methods, and they need to be formal because they are part of formal legislation. I haven't covered a lot of stuff. I haven't talked about the Australian standard method, which is quite detailed, but I've given you a link there to have a look at the Australian standard soil carbon method. There's a lot of detail there, but I think there's a lot to be learned by studying it. I haven't talked about fancy ways of constructing the strata, but that's what the patent that Buddy talked about earlier is about. And of course, patents are about commercial applications, but if you're doing research, anybody can use these methods, and I encourage them to do. And of course, I haven't talked about the forms of soil carbon. We've been largely talking about organic carbon, but particularly in places like Australia, I think it's crazy to credit organic carbon gains if at the same time we're losing inorganic carbon through irrigation or other methods, or climate change itself. So we need to take into account the different forms of soil carbon in the overall scheme of things. Whether ICCC believes in it or not, as a soil scientist, I believe in it. Anyway, conclusion about soil carbon counts. It does count. Going back to the beginning, how to put more carbon into the soil and keep it there. For me, at the moment, this is the biggest issue and needs the most work. We haven't thought of a new way of doing this for 50 years, and as soil scientists, we need to actually work on that. How to demonstrate that has been done? Well, that's what we're talking about today. It's still an important issue, of course. I think there are a few key questions remaining around the uncertainty and how we can integrate all the different methods. But I think we're well on the way, and I think Pete's talk made me confident about that. We're well on the way to solving this efficiently with a known precision. And with that, I'll thank you very much. Thanks for listening.
Okay, thanks, Alex. So maybe we have run out of time. Maybe we start with a discussion. So I'll invite Lady Stella Kutika. Lady is a soil scientist at the CRDPI in Pontoa at the Republic of Congo, and she will be our discussant today. So over to you, Lady.
Yeah, thank you, Buddy. Thank you for the great presentation to both of you, Pete and Alex. So we discussed about MRV. This, of course, directed for landowners and farmers so they can obtain carbon credit and payment for good soil management. So I have a question to Pete, and which will be the same to Alex as well. In your approach, who will be responsible of carrying out MRV? Are there three tasks performed by the same individual or organization? So the same question for Pete and to Alex.
So I can start with that, Lady Stella. So I think the measurements will be taken on the farm. So that will be the farmer's job to either do those measurements or to get them taken. They would get somebody in to, a consultant in to take the soil samples and to send those samples off and measure them. But the verification, I think, has to be done by an external party. So if they're selling it for carbon credits, that external party would be whoever was providing the carbon credits. If it's for some other program if it's under national incentives to do that, then it would be some other organisation that was appointed by the national government. So I think if the soil carbon sequestration is contributing, an NDC, for example, a nationally determined contribution, it would be up to the government to put something in place to make sure that the farmer's done what they've said they've done, and that they've increased the carbon to the extent that they said they've increased the carbon. So it's different people doing the monitoring, the reporting, and the verification, but the measurements have to be on farm.
Maybe I can add a little bit. So I think one important issue is that the unit of measurement and verification should be the farm, the whole farm, and not a particular field on a farm, because I think otherwise people just move carbon around, or there's a temptation to do that. So that I think the measurement unit or the verification unit is important. In Australia, I give the Australian example. If we were creating a non-government accreditation scheme, what Pete says probably it is fine. It may be practice-based, it may be measurement-based, and could be done by the farmer. Most more scientific or technical aspects of agriculture in Australia is done by consultants. Consultants who work for 10 or 20 or 50 farmers and help with all their work. When it comes to creating Australian carbon credit units, which is a government scheme, this is what the whole Australian soil carbon methodology is about. There would be independent auditors doing this work, and that's part of the reason why I worked on the sampling methods, because I do think you need independent auditing. And one of the reasons why we use stratified random sampling is we do it in a way that we don't measure at the same location in the second round, so that the landholder doesn't actually know where the measurements are being taken. So that's part of the methodology. But it depends on what scheme we're doing this for. But if we're doing something for the government where the government is reporting those results internationally, I think we need a very formal scheme and we need independent auditing. I think that agrees exactly with what Pete said.
Yeah, okay, thank you. So here another question to Pete. you introduce a system from RFV that incorporates remote sensing and modeling. Who or which organization will be responsible for operating such a system?
Again, that depends on who's interested in the answer. So I think it would be most effective at the national level if we have national MRV systems. I've mentioned that a lot of countries already have a bunch of this capacity. They have modeling capacity, they have some long-term experiments, they have some short-term experiments, but none of this has been pulled together. They have remote sensing, but none of this has been pulled together. So I think it would be best done at the national level to get a national level audit to verify what's going on in the national greenhouse gas industry. But you may also require different audits, different MRV for carbon credits. So that would obviously be the organisation that's providing the carbon credits. They could be the person that were accessing that. It should be done independently, but they could be accessing that information for the carbon credits. So I think and then of course there's the global. I mentioned the Rexoil program that FAO are setting up, where individual governments are going to be sending in their results into the Rexoil program, which will start to put together a global picture. But each one of those estimates have been done at the national level by local experts. So I think that's also important to get local expertise in, and not to have just a top-down assessment done globally with potentially a lack of understanding about the situation that goes on within farming within those individual countries.
Thank you. Alex, so who will be the organization responsible for auditing process? What do you think, government or private companies?
Well, once again, I do it from an Australian point of view. The answer would be both. The government would be responsible to some degree, but I think most of the work will be done by private sector organisations, including the ag sector. And I think that's why it's important in the methodologies that we use that there is calibration sampling happening, because that's what gives us the idea about the precision of remote sensing estimates or other kinds of modelling estimates or measurement estimates. So I would say, yes, some national overview, Department of Climate Change probably, who are most responsible for this, but much of the work will be handed over to the private sector, and they will be tasked with providing evidence of the measurement and the uncertainty. So it's both, I think.
Okay, thank you. But for now, I'm going to be a little bit a troublemaker. So, Alex, you advocated for measurement, both in the country like mine, certain country, and you could see very well for the presentation and the map, Pete showed us that in certain part, we have the place we are lacking measurement. And ironically, I will say, these are the very individual who benefit for the most for this practice to enhance soil carbon. So how will your approach be applicable in this country, central country, where we could see that we are lacking even data?
That's why we invented digital soil mapping, so we could do this. And dynamic digital soil mapping. So we understand that in some areas and at some scales, it's not possible to do all the measurements, but it is possible to do digital soil mapping, and it is possible to estimate the uncertainty of that. Now, the uncertainties may be large, but at the national scale, at least we've got an estimate. So in a sense, we've kind of solved that problem. There hasn't been enough work on the dynamic digital soil mapping. There hasn't been enough work on combining the sort of modelling that Pete does with the digital soil mapping, and there's more to be done there. But I think at a national scale, that is the approach for many parts of the world, at least in the first instance.
Yeah, but in some part of an individual map, I think they do not have. So now I have a question to both of you. It's a little much more, I know that we talk a little bit about that, but as a scientist, how about the various types of carbon, such as labile, decomposable carbon, versus more persistent form? Understanding the distinction between this carbon form can provide valuable insight into carbon cycle and its impact on ecosystems. So, I mean, how can you, I can rephrase it, how can you try to locate both type of form of carbon in the approach we have been talking during this webinar? Labile and more persistent fraction.
Yeah,
yeah.
I'll take that one first, and then I'll hand over to Alex because he's more expert in this. I think
good one.
Measuring the different fractions is important and can be useful. I mean, ultimately, it's the total carbon that we're interested in, because we don't want to just be measuring one fraction and ignoring another, because that could give an undue an unfair indication of how much carbon is removed. The reason we're doing soil carbon sequestration is partly for fertility, but it's partly to remove carbon dioxide from the atmosphere. So we want to know the total amount that's removed from the atmosphere. So for that, we have to know the total carbon. But it's important, as you said, to understand the dynamics. So measuring those different fractions is important. So the mineral associated organic matter that's been proposed more recently as one that can be used. But there are other forms of fractionation that we can do that tie into the model pools that we can use as model for initializing the models and for verifying the models. So it's really important to do those things, but the total carbon has to be the ultimate measure that we're using, because that's going to tell us how much has been stored in the soil for a given period and removed from the atmosphere. Over to you, Alex.
I don't think it's, I mean, Pete's definitely the expert on this, so he's been modeling this for forever. So I agree. I think it's important to know what, if we believe that these fractions exist, it's good to try and estimate them, but it's the total that's important. I think there is some possibility with spectroscopy to get at some of these fractions, but there will be a large uncertainty on the proportional estimates, I think. As I said in my talk, we're not looking at calcium carbonate, and we should be, because in Australia, for example, we're gaining calcium carbonate in some places where it's drying out, but in other places where we're doing irrigation, we're actually losing calcium carbonate. So we do need to bring this in. We need to bring this to bear, as well as the organic carbon.
Yeah, thank you. I'm almost done, but I will have a little bit provocative question, yeah, as scientists. I know I'm myself from 4 per 1,000 initiative. What do you think, both of you? Are you giving too much value on carbon alone? It's not essential to recognize that carbon is just one element contributing to the creation of healthy soils. You know all about stoichiometric relation to carbon and to nitrogen and phosphorus, for example, which serve a mutual function of soils. Perhaps we must consider shifting our focus towards compensating farmers for ecosystem services, for instance, rather than only being concentrated of carbon. I think the broader perspective will lead to more comprehensive and sustainable soil management strategies. I will finish by that. When you go in most part, in certain part, when you speak about carbon, no one will pay attention to that. They are much more focused on benefits or ecosystem services. And I was lucky during the summit of the tree basin in my country last month. There are someone for Frances for World Resource Institute who give very good speech, webinar, I mean, not just carbon capturing all benefits of forests for stabilizing, I mean, climate for local to global scales. So during this presentation, they were trying to show how it's important when it came to both altogether fight things like climate change. We need to introduce also other factors. How do you think, both of you? Are you focusing too much on carbon, or maybe to make it more available or comprehensive for people, especially in this part of the world where we could see on the map we have less data, to maybe try to introduce ecosystem services and also other benefits rather than carbon alone? So to both of the question, and then I will have the very last one. Yeah.
Thank you. I think you've answered your own question there, Lydie Stella. I think it's really important that we don't just focus on soil carbon, because I mean, soil carbon, the reason for focusing on soil carbon, as I mentioned, if you're interested in the amount of carbon removed from the atmosphere, then it's the amount of carbon that you're interested in. But soils are so much more than soil carbon, and the soil health is really important. So what's important to the farmer isn't necessarily how much carbon's been removed, it's the health of the soil. But because the carbon is held in the soil organic matter, and the soil organic matter is a headline indicator of soil health. So in a way, there's a link between soil carbon and soil health. So improving your soil carbon should be improving your organic matter, which should be improving your soil health. So the two things are related, but I think there is too much of a focus on carbon and carbon markets, and we should be thinking in a more rounded manner about soil health and the ecosystem services that are provided by the soils. I quite agree with you, and I think you answered your own question there.
Alex,
can I add anything? Okay. Of course, this is why I work on soil security, which is it's a wider concept than soil health. We call what people call soil health, we call it soil condition. Look, there's no doubt that soil carbon contributes to several soil functions. It diminishes several threats to soil, and it provides soil services. I also use the term soil services, not ecosystem services, because soil provides services to our global existential challenges, such as climate change or loss of biodiversity, or water security, or energy security. So there is probably too much attention in soil science to soil carbon at the moment, and we need to focus on a wider range of things. But there's no doubt that soil carbon is important in the ecosystem. It's important for production. It's important for soil health or condition for a range of soil functions. So I think I'm 50-50 on this one, bit of both, I think.
Yeah, thank you very much. So I'm almost done. What I'm going to say is the very last, is just link it to what your response. So what do you think? What can be done to make MRV more appealing for kind of small holders I'm talking you about, the one who do not know about carbon? So what can you think making more appealing so they can be interesting on what you have been talking about? That's really the very last question. What do you think about?
Can I take this first again, Alex?
Yeah, sure.
Okay. So I think I don't think we'd really make it appealing to the farmer. I mean, why does the farmer want to do this? All the farmer cares about is having good soil and improving their profitability, productivity, and improving their livelihoods. So I don't think the burden of MRV should be placed upon the farmer unless the farmer is claiming something. If they're receiving a payment for the carbon or for the soil health or the ecosystem services that they're providing, then they could be asked to provide also to get those samples and to get that verification in place if they're receiving money. but it should only be a proportion of that money that they receive. So they should get a net benefit from doing so. So there shouldn't be an additional burden that's put on the farmer. This should be, as I said, at the government level. This is something that's done independently of the farmer. And as Alex said, this is quite often done by independent consultants in Australia and other countries. So it shouldn't really be the burden of the farmer. But improving soil health is of benefit to the farmer. So anything that we can do to help the farmer improve their soil health will also improve the greenhouse gas inventory of the country, and will also benefit the productivity and the fertility of the soil and improve the agricultural output of that country. So I think it has to be the national governments that put that money in. And for countries that don't have the ability to pay that money, then there should be a flow of finance from the countries that can afford to do that.
Yeah, but I mean, this is a good question, and to my mind, not a somewhat difficult question. Sitting on a committee, a government committee on this, if I wasn't sitting on the committee, I would simply say, make it as simple as possible. In other words, accept the uncertainty, but as Pete says, encourage practices which we think will sequester more carbon, or more importantly, will improve soil condition and soil functionality. I think that's what we need to try and do. But governments have to report internationally, and therefore they have some constraints. They need to be able to believe that the numbers that they're reporting are correct. So there's the kind of tension in there. I think in the future, maybe 10, 20 years, certainly in places like Australia, doing soil carbon sequestration will be part and parcel of our agricultural system, because we are signed up for a net zero agriculture. So insetting soil carbon will be part of that, and we will not be able to export our agricultural products without doing that in the future. So it will become part of the future, I think. To what degree will be detailed measurement remains to be seen, I think.
Yeah. Okay, thank you. I will give the lead to Budi, but what I want to say to finish the part is in 10 years, maybe we'll have the same map than Pete showed us in this way, because the country where we need to have value, unfortunately, all of us cannot resolve this problem. And then in 20 years or 10 years, it'll be the same problem. We lack the data in some part of the world. And that is a pity, because it's a place where people need to benefit of that. Thank you. I will give it back to Budi.
Okay, thanks, Liddy. Yeah, so yeah, we ran out of time. We almost more than 1 hour. So I'll sorry for we can't answer all the questions, but maybe I'll close with a question to you both. The COP28 will start very soon on the 1st of December. And Pete, you've been around for this since I think Kyoto Protocol and until COP21. So now we are up to COP28. I see that soil is not mentioned, but it says that there is a new framework for a new deal of finance, and they talk about transformation of our food system and agriculture. So what do you expect of COP28 that would benefit soil or soil carbon?
Well, I hope that there's something that comes out of COP to benefit soils, but soils aren't the answer to climate change. They can make a small contribution. So we've just got to cut our fossil fuel emissions, and all this messing around by politicians, avoiding the issue and enabling the continuing use of fossil fuels is absolutely not what we need. We're in a climate emergency, and it's time that the governments of the world understood this. I think they understand it, and they stopped new oil exploration, and they stopped subsidizing fossil fuels to the extent that they are. So I think this is the fundamental thing. We can make a contribution with the soils. We can draw down a certain amount of CO2, but unless we reduce our fossil fuel emissions, really, really significantly. They have to peak like very soon and then rapidly decline over the next couple of decades. Then we're not going to be able to meet our Paris targets, and no amount of soil carbon sequestration is going to do that. So I think that the real focus has to be on cutting fossil fuels and getting really serious about it. It's getting too late in the day to be messing around with other things. Let's hope the soils can be in there somewhere, but I think we have an existential threat on our hands that needs to be solved.
Thanks, Alex.
Well, certainly climate change is a global existential challenge for sure. And I completely agree with what Pete said. I think, can I add anything? Probably as an agriculturalist, to say that we need some recognition and some targets for what I've called net zero agriculture. In other words, creating agricultural systems that are net zero, which means, you know, the fossil fuels and the fertilizers are not coming from the fuel for agriculture and the fertilizers are not coming from fossil fuels producing greenhouse gases, but are produced locally and on farms. And we need to move to technologies that allow that. And that's why we need some targets around net zero agriculture. So when we have our hydrogen tractors and wheat plants that can fix their own nitrogen, we'll be well on the way. Things like that. But we need targets around that.
Okay, thanks, everyone. Thanks, Pete. Thanks, Alex. So we have a great discussion, and I hope we're all going to move forward with the MRV, and we'll hope for that we have a great outcome from COP28. So good evening, have a good day, and see you, everyone. So the recording will be made available in a couple of days from the 4 per Meal initiative. Thank you, everyone.
Thanks, everyone. It's good. See you later. All the best.
Ciao, ciao.